See this one example of converting the time signal into frequency domain. This is the time signal f of t. So this signal varies with the time. This signal has two frequencies. First frequency 100 and second frequency 200. It has amplitude of 0.5 for the second frequency and 1 for the first signal, right? So here fs is the sampling frequency, say 2000 hertz, and number of samples 256, and time step is 1 divided by 2000.005 seconds. And f1, that's the first one, 100 hertz, and f2 is second tone, 300 hertz of amplitude. Next, and if you can go with the time signal for the sample 1, and if you put it in the time 0, f of t is 0 and 0.005, it's going to vary 1.294. Then with 0.02, it's going with minus 1.294. Then it can go 1.294, like it varies, right? So it's like going up and down. Then the signal wiggles up and down. You can already see that it's not a pure sine, it's a sum of two, so the shape is like a little distorted. You can see like this little distorted, the shape is like this kind of little distorted shape is there. Okay, this is like this kind of little distorted shape, you can see that. So you can see this kind of signal. This signal has two frequencies, one is 100 hertz and one is 300 hertz, and amplitude 0.5 and 1. Okay, so at 0.001 it becomes 1.0269, right? 1.294, 0.001, and 0.0005. If you see 0.0005, there is this value. This goes minus 1.2. Right, it varies in between. It goes up and down. So it repeats that pattern. Then next one, if you see the frequency bins, if you take the for a discrete Fourier transform with n equal to 56 sampling rate 2000, then frequency bin represents fs divided by n is 7.8125 hertz. So bin 1 is 0 hertz, bin 2 is 7.8, bin 3 15.6, and so on. And then expected Fourier transform, if you see the our signal has two components, right? Main components 100 hertz and 300 hertz. So let's locate which bins those fall into. So 100 where it going to fall. So 100 divided by each bin is 7.2. So it's going to be around some 13th bin. It's going to get a peak, and 38th also it's going to get another peak. So we expect peaks around bins 13 and 38. Numerical magnitudes, concepts of results, if you see bin 1 to bin 13 we are getting 120, that's the main peak, that's the magnitude one, and another is 64. So this is almost proportional to the amplitude. This amplitude 1 means next amplitude is 50, half of that, so it becomes 64. So if you see this one at 100 hertz amplitude 1, so main tone of the string, 300 hertz amplitude is 0.5, harmonic higher overtone, all other frequencies 0, not present the vibration. This confirms that our original time signal, which looked messy, is actually made of two clean sine waves. Exactly what the Fourier transform reveals. What's the time column shows how the string moves. Frequency column shows what nodes it connects. So if you see signal is this one, that there's a main node of 100 hertz and smaller overtone is 300, and with the direct Fourier transform, like a real part and imaginary part combined to give magnitude. At 100 hertz, the magnitude is largest because that's the sign, that sign is strongest, amplitude 1, and 300 magnitude is smaller, amplitude is 0.5. So the magnitude is proportional to the amplitude of the frequency in the original signal. Magnitude numbers, if 100 is the frequency and magnitude, you can see 128 real, imaginary 0. So main peak has magnitude of 128 strongest vibration, and second peak has a magnitude of 64 weaker vibration. All other frequencies has 0 magnitude, that means not present. Physical meaning is that magnitude, how much of the sine wave is present in the string vibration. Magnitude shows how much of the sine wave is present in the string vibration. Higher magnitude means louder, stronger note. Lower magnitude means weaker overtone. Zero magnitude means the frequency is absent. Here you could see these values. This is the time varying from time signal 0 to increasing to its 256 bins, right? 256 samples. So that's what we have seen, like, so 0.125 until that, and this value is the f of t value, the functional value. You can see it varies, that signal f of t. And frequency, we know each bin is 7.825 multiples of that, and the magnitude for that one. So this is the time signal. This is the time signal, and that time signal is converted into time domain is converted into the frequency domain. So here this signal consists of two main frequencies. That's how it's related to each other. So here we can see this Fourier transform in the VBA code. So the parameters what we are using is n, fs, frequency, and the integer. So fs is the sampling frequency 2000. Number of samples is 256 points, and we can get the time period 1 divided by frequency. And these are the arrays we are making it. Frequency 1 to n, and real number, imaginary number, and magnitude. So first to generate the signal, so we are generating the signal. So f of t, that basically t is sine 2 pi into 100t minus then plus 0.5 is another magnitude next signal sine 2 pi into oxytocin and 300t. So it's a loop, it will go for until n is 256. So until that point it goes, then it generates a signal. Then we are doing the Fourier transform. In Fourier transform, we need to get the real and imaginary number. So real is the uh, real number and plus f of I into cos 2 pi into k minus 1 to I minus 1 by n. So we can get the real, this magnitude, and the real and imaginary. So we can get the magnitude square root of these two, and output we can get it. The output we will put it in the Fourier, and is the name of that. Clear that the signal in range A1 column we are putting the time signal, B1 column we are putting the signal, D1 is frequency and magnitude. So write the time domain data, it's writing the time domain data, and then frequency domain data also, it's only first half we are putting it, until n by 2 we are putting it, and the magnitude is written here and frequency is written here. That's what we have seen here. That's what exactly it's seen here, the output of that. Here time and signal value and frequency, and then magnitude. We know how this frequency is coming. That's each bin, that 256 points are that 2000 divided by 256. So we can get 2000 divided by 256. That's 1.825 by, that's the bin. So we know at 13th bin, that is 13th bin, we are getting the higher magnitude. That's this one, that 101 you can see here, it's almost 120, that's the magnitude. And one more also for the next frequency we are getting in the 38th bin. So 38th bin you can see it's 296, right? So if you go down here, 296, where is that coming? Yeah, 296, yes, this is 48, almost 50. That's where we are getting it, this frequency. Here we are getting it. So what is the value? The peak value you can see. This is the first peak value, it's 120 magnitude. This is second peak value, it's 48.9, point number 296.875. So two frequencies are in the signal. So Fourier transform tells us how many frequencies inside the time signal. So we will discuss like a group discussion. Oh, wow, what is that sound? This is the sound basically they say a signal. Why is it wiggling like that? I see a vibration, but I can't tell what note it is playing. Can anyone hear them? Can we see it somehow? Yes, I can look at the vibration in a magical way. I can split into I can split into all its notes. Split it how? Is it like rainbow? It's just like sunlight becomes a rainbow. A complex vibration becomes separate frequencies. Each frequency has a strength. Who wants to see? There is a big number here, 128, and another smaller 164. What do they mean? These numbers are called magnitudes. They tell us how strong each note is. Why one is bigger than the other? Why one is bigger than the other? Why is one is bigger than the other? A string is vibrating mostly at 100 hertz. That's why 128 is big, but it also vibrates little at 300 hertz. That's why 64 smaller. Can you see which note is louder? Yes, 100 hertz is louder, but why are there tiny numbers here and there? Those are whispers of energy spilling over. The notes are not perfectly aligned with magical boxes. Do you think we can fix it? Maybe if we stretch the string a little, use a magic window, the tiny numbers will vanish. Does that make sense? So the big ones are the real notes and the little peaks are just noise. Can anyone tell me what the main melody of this string is? It's 100 hertz with a tiny echo of 300 hertz. Now everyone knows my secret song. Can we make it louder? Can we play more notes? What did we learn from this? Each vibration has hidden notes. Fourier can find them. Magnitudes tell us how strong each note is. Tiny numbers can appear due to imperfect alignment. Number frequencies like the color of the vibration. Magnitude is like brightness. Phase is timing. Can you imagine that? Can we see another string? You also dance to my new tune. So vibration is what you see. Fourier detect the finding hidden notes. Detective finding. How strong each note is, magnitude, tiny numbers, leakage of rounding errors.